Welcome back to AI Codecast. Today, we're going deep on a pretty interesting coding problem, the LRU cache. You ever think about like how your web browser figures out which pages to keep loaded so they pop up super fast?
Hmm.
Or like how your phone makes sure your favorite apps run smooth?
Hmm.
Well, it's all thanks to this clever thing called caching. And today, we're going to break down one of the most popular ways to do it, the least recently used, or LRU cache.
It's funny because the LRU cache isn't just some abstract computer science thing.
Right.
It's a way of solving problems that you can totally use in real life too.
Yeah.
Imagine you're trying to get your closet organized, but you don't have much space.
Oh, yeah.
You'd probably keep the clothes you wear all the time easy to grab, right?
Totally.
And then maybe tuck away those things you haven't touched in ages.
Yeah,
That's LRU in action, putting the stuff you use most front and center.
makes total sense. So we're all about efficiency here. But before we get all into solutions, let's make sure we're all on the same page about what the problem actually is.
Yeah.
Imagine you have like a storage box, a cache,
Yeah.
but it has a fixed size. Let's say it can only hold 5 things. You can put stuff in, take stuff out, but here's the catch.
Right.
When the box is full and you want to add something new,
Mm-hmm.
you have to get rid of the item you used least recently to make space.
Exactly. And to make it even trickier, we want to be able to add and get things super fast. We're talking like instant, no matter how many things are already in the cache.
Yeah.
In the world of algorithms, that's what we call O1, complexity, the gold standard for speed.
Okay, so we've got our box, limited space, and the need for speed. Now, if you were tackling this, where would you even begin? Any simple way to approach this, even if it's not the most, elegant solution?
Well, you could try using a simple list to store the items and just note when each item was last used.
Yeah.
Whenever you need to add a new item and the cache is full,
Yeah.
you go through that list and find the least recently used one and boot it out.
That sounds straightforward enough. But wouldn't going through that list get really slow if our cache was packed with items?
Yeah, you're right. That's the problem with just going with the first thing that comes to mind. As the cache grows, finding that least recently used item takes forever.
Right.
That linear search time is complexity and being how many things are in the cache, and that's way too slow.
Okay, so a plain list is out. We need something smarter, something that lets us find and evict things super quick. What if we could, instantly know which item was used least recently without checking the whole cache?
Now you're thinking, we need some way to keep things in order. How about a queue where the least recently used item is always at the front, ready to go?
A queue is interesting, but how would we quickly find a specific item inside the queue to update it? Remember, we need to both access and evict instantly.
Good point. You've hit on a big challenge. A simple queue alone isn't going to cut it. We need a way to have super fast lookup A and D keep things in the right order.
Yeah, that's a tricky one.
Let's take a second to think about this.
All right, listeners, we've set up the LRU cache problem and hit a bit of a snag with our first ideas. But don't go anywhere. We'll be back in a jiffy with the secrets that make this algorithm really sing.
We'll crack this, don't worry. So remember how we were struggling to find a way to quickly access A and D manage the order of items in our LRU cache?
Oh yeah, the queue was great for knowing what to evict, but actually finding a specific item fast was a problem. It was like we were missing a piece.
Well, what if I told you we could use TWO data structures together to crack this?
Okay.
Imagine combining a super fast lookup table with a clever way to keep things in order.
Right.
Think about a library. You have a catalog to find books, right?
Yeah.
And then the books themselves are organized on shelves.
Right.
What if we did something like that for our LRU cache?
Ooh, I like where you're going with this.
Yeah.
So you're saying use something like a dictionary to store the keys and values, but then have a separate thing to keep track of the order they were used.
Exactly. That's the winning combo. A hash map for super speedy lookups and a doubly linked list to manage the order.
Oh.
The hash maps our catalog, give it a key, it instantly tells you where the value is.
Okay.
And the doubly linked list, that's our library shelf.
Gotcha.
Most recently used items up front, least recently used at the back.
Okay, I think I'm starting to see the light here. So walk me through this.
Yeah.
Say we get a request to access a specific item in the cache.
Okay.
What happens first?
First, we hit up our hash map. Does this key exist?
Right.
Remember, hash maps are crazy fast, so
Yeah.
this check is instant. If we find the key, it tells us exactly where the matching node is in our linked list.
So we use the hash map like a shortcut to jump right to the spot in the linked list. And then what?
Once we've got that node, we got to update its position, right?
Yeah.
Show that it was just used.
Yeah.
So we move it to the front of the linked list.
Okay.
Now it's the most recently used item. Kind of like when you borrow a book from the library.
It goes back on a special shelf for recent borrows.
Got it. So get requests, those are handled by the hash map to find the item, and then the linked list to shuffle its position.
Yep.
Seems pretty smooth. But what about when we need to add something brand new?
Adding new items is where it gets interesting. First, same as before, we check, is this key already in the hash map?
Okay.
If it is, we just update the value
Right.
and with a GET request, move that node to the front of the line.
So far, so good. But what if the key is new and our cache is already full? That's where we got to make room, right? That's the whole eviction thing.
Exactly. Cache is full, new key, got to clear some space.
Yeah.
Remember our trusty doubly linked list?
Uh-huh.
Least recently used item is always chilling at the end.
Right.
So we just kick it out. Gone from the linked list, gone from the hash map.
Okay.
Then we add our shiny new item to the front of the linked list and tell the hash map, hey, this is where this new guy lives now.
This is so smart. Combining a hash map AND, a linked list, we've made a system that's fast to access AD, efficient at kicking stuff out.
Right.
And we're hitting our speed target because both get and put operations are, on average, constant time.
Exactly. It's pretty slick, huh?
It is. It's like having your cake and eating it too.
Now, building this from scratch, that can be a bit of a headache.
Oh, yeah, I bet.
Especially dealing with all those pointers in the linked list. But good news.
What's that?
Lots of programming languages have built-in things that can make our lives way easier.
Oh, you're speaking my language.
Wouldn't you like to know if there's an even simpler way?
Of course. Tell me everything. What kind of magic can these built-in data structures do? All right, spill the beans. What kind of built-in data structures are we talking about here?
Okay, so let's say you're using Python. There's this awesome thing called OrderDict.
Okay.
It's like a regular dictionary, but it's got this superpower. It remembers the order things were added in.
Oh.
It's basically a dictionary that manages our linked list for us behind the scenes.
Wait, so we don't even have to mess with building a linked list ourselves?
Nope.
That sounds almost too good to be true.
With an OrderDict, when you access something, it automatically shuffles itself to the end, so it's the most recently used. And when you add something new, same thing, it goes to the end. Plus, if your cache is full, OrderDict has this popitum method that removes the very first item, the least recently used one.
Really?
Exactly what we need. Super elegant, super efficient.
So OrderDict just takes care of all the hard work, and we can just focus on the logic of our LRU cache?
Pretty much.
That's awesome.
Yeah.
What about other languages? Do they have similar tools?
Totally. Java has something called linked hash map.
Okay.
Same idea, hash map plus a linked list. Makes building an LRU cache super easy.
Nice.
And C++ doesn't have an exact match, but you can still pull it off by combining a std.list with a regular hash map.
So no matter what language you're working with, there's probably a way to use these built-in data structures to make your life easier with LRU cache.
Exactly. It's all about knowing the tools you have. Sometimes the smartest solution is using the right pre-built stuff instead of starting from scratch.
Right.
But even when you're using these handy tools, it's super important to get how they work under the hood.
Yeah.
That way you can really understand why they're so powerful.
Yeah.
And you can fix problems if they pop up.
That makes a lot of sense. Knowing the inner workings gives you the power to choose the best approach for any situation.
Right.
So, quick recap. We've looked at two main ways to solve the LRU cache problem. The manual way, with the hash map and doubly linked list, and the easier way, using built-in stuff like OrderDict and linked hash map.
Yep.
Both work, but with different levels of complexity and control.
Exactly. Doing it manually, that gives you a deeper understanding of how it all fits together. But the built-in options, those are super convenient, and they often run faster because they're optimized for that specific language.
Right, right.
So the best choice really depends on what you're trying to do.
Before we wrap up, I had one last thought. What if we didn't just kick things out based on how recently they were used, but also how often they get accessed? Like, there might be some items that don't get used all the time, but they're so important that we want to keep them around longer.
I see what you mean.
Yeah.
That's a really cool idea. And it brings up something called the LFU cache, which stands for least frequently used cache.
Oh, interesting.
It's like LRU, but it considers both how often some things use AND, how recently.
Makes sense.
It's a bit more complex, but it gives you even more control over what stays and what goes.
So much to explore in the world of caching algorithms. Listeners, if you're feeling inspired, I challenge you to try building these solutions yourself. play around with different data and cache sizes.
Yeah.
Maybe even come up with your own twists on the LRU theme.
Keep that curiosity going. And remember, the most important thing is to grasp the core ideas.
Absolutely.
Once you have those down, you can use these techniques to solve all sorts of problems.
Until next time on AI Codecast, happy coding.